first off, let's look at the problem. See what we have. Okay? So, the thing about these problems is that they are not just going to concern with charges and electromagnetism that you're going to cover during this semester. They are going to have portions of statics that you have covered, dynamics that you have covered. So all of these things they are going to come and play a role in your problems. Okay? So you will probably have to remind and use some of the things that you have used last semester. So question number 15. So first off, what is the problem? Let's try to get a feel about the problem. You have two spheres like this. They're hanging from a string. They didn't do a good symmetrical job. And mind you, my drawing capacity is it's not really flattering. But hey, I hope I can make sense. That's what matters. Okay, we have two spheres. And also, we are given the length (30 centimeters). How many? Yeah, how much is that in meters? By 3. Exactly. Mass is also given. And what is the mass?
2 grams.
I'm sorry?
It's 2 grams.
0.2 grams, right?
Yeah.
So 2.20 grams. And how much is that in kilograms? Using powers. Okay, what else? The angle is given to us with the vertical. So this line is the vertical for me. So I'm going to put a simple theta, and that is given to us as 5 degrees. Right? I guess that's pretty much it. Okay. So let's look at this problem. So what do we have to find out of this? Out of all these variables, values that are given to us, what do we have to find? We have to find the charge. We have to find the charge of these spheres. Now, let's go over and try to understand the problem. So obviously these two spheres are charged. Okay? They are charged. And they are charged with the same kind of charge. So the same kind always going to repulse each other. Good? Right. So that is why they are just kind of hanging like this, and they are stable, stationary, in equilibrium. Okay? So in order to hold a mass, however small it is, you need to have an applied force pushing it sideways. So in other words, we have a force that we can say acting this way. be F. I'm going to focus on one mass. Obviously, whatever we have is going to be the same for the other mass. The force is going to change its direction, obviously. Apart from that, everything pretty much is going to be the same. Okay? So if I go to draw, I have a force here. And then there's another thing. We have two forces now. We have a weight that is pushing the mass down. A force, what we can say clearly, electrostatic repulsion, pushing this mass this way. They are pushing each other, equal and opposite forces, because each of these have the same charge. Each is going to push the other, and by doing so, they themselves are going to be pushed. You apply a force, and you have a reverse force applying against you. This is what happens to each of these masses. Okay, so what else? What else do we have? We have a tension working upward. Just because of these two forces, you cannot make this mass stay in the same place. Obvious, because the two forces are going to be working this way and this way. If you have two forces like this, you will have a resultant force acting this way. Guess what? This is going to go this way. So we need a third force to balance this, and that obviously is our tension. Same goes in this direction. Attention. So what we have right now is our free body diagram. Free body diagram. Good, right? Things look good so far. So now comes your high school geometry, right? So we have to figure out a couple of angles. Actually, one should do the trick. So we have an angle right here. Both angles are going to be theta, and both are going to be 5 degrees, symmetrical. So if that angle is theta, what is this angle? I'm giving you the answer. Theta. Bad question, right? So obvious. But this is theta from geometry, right? Because these two lines are parallel to each other. If you have two parallel lines, a line intersecting them both, then these two angles are going to be exactly the same from geometry. So we have this angle as theta. We have a tension, we have a force, we have a weight. First off, this particle, this mass is stable, stationary, like I said. So in other words, what can we say about the forces? No acceleration. In other words, the net force is 0. However, we are smarter than this. We know how to use this information to our advantage. What we are going to do is we are going to use this information in two different directions. In x direction and in y direction. That will help us to solve and get many different equations which we will solve. That will give us our Q. This is what we are going to find. Right? Okay, let's look. First off, let's say this is A. Let's say this is B. I just want to name things. I like that. Okay. So let's see. Let's put this as sphere A. Oh, mass. And let's say mass A. In equilibrium, it mean? Now, each of the professors or your instructors you met have different conventions. This is my convention. Okay? Dr. G may have a slightly different variation of it. This is mine. So what I'm saying right here is this is my positive direction in x-axis. That's one. And this says all of the forces, sum in the x direction, going to be 0 because of the equilibrium. Okay. Good. So question, if you have any questions, stop and ask. Good. So now we have to resolve our forces. We have our x-axis this way. This is our positive x. So we can say 0 because the sum has to be equal to 0. Start with a 0. Then tell me what force works in x direction positively and how can I get that? Is there any force or forces working in or acting on positive x direction? Yes.
The tension.
Tension. That's exactly right. So if I resolve the tension, the component going upward vertically will be T cos theta. T cos theta. The component going in positive x direction is therefore T sin theta. Now I love to keep my symbols. You will see that. There's a reason for that. Because it's easy to manipulate symbols rather than numbers. If you have a 3-digit number, you have to write 3 times plus the point. That's 4 things you have to write. That means probabilistically you can make 4 mistakes. Remember that. Every time you add something, you can make a mistake. So having a symbol well defined reduces chances of I am making any mistakes. Okay, this is what I'm going to do. So now I have T sin theta. What would work on the negative x direction? F. It's okay to make mistakes, guys. If you know everything, you're not going to be here, right? Let's be honest, right? Why do you have to come to class, right? You'll never see me. You'll do everything outside, right? So let's make mistakes. Let's learn. It's okay. It's the whole purpose. So this is T sin theta minus F. So out of this, I can immediately write T, rather I will switch F equals T sin. I can take F to the other side. So if I take F to the other side, F becomes positive. This is still positive, so I have F equals T sin theta. Okay, let's put a formula number 1. Let's look at what do we know. We don't know anything about this guy. We don't know. We actually don't know about this too. Please, this part. We know about this. Absolutely, because theta is given. In order to find the charge, we know there is a formula that gives, if the charges are given, you can calculate the force. So direct, straightforward formula. And it is by far one of the very first formulas you learn. So that we know. So that means we need to have F figured out eventually. This is very important. So let's put that, kind of mark it. Okay? You don't have to use my symbols, by the way. Okay? I'm just going slowly so that you can follow me. That's the whole purpose. Okay? So there should be a method to my madness, right? Otherwise, we'll all be mad. So that's bad. So let's see. Let's look at the other axis, y-axis. So I have sigma Fy equals to 0. Again in equilibrium. So tell me a force acting in positive y direction. Yes. Tension. And now let's go one step more. Cosine of the tension. Beautiful. T cos theta. What would work on the negative direction? mg. So we will take this out onto the other side. I have mg equals t cos theta. Second formula, or rather equation. Again, we know m, it's given to us, so easy. Cos theta, obviously, theta is given to us, so easy. Only thing that we don't know is t. We have two formulas or two equations. Now, first off, do we really need to find t? Is it asked in the question anywhere? No. You can find it. Absolutely. But if you are not being asked to find something, why do you have to waste the time, right? Especially in an exam or something. Of course, when you do this at home, you will find it, right? You are very good students, I know. You stay awake and solve all the problems. You're my students, right? I know. So let's see, how do we figure this out? And get rid of t because we know how to find that, right? So what we do is we divide 1 by 2. So if I do this, I get f divided by mg on the left side. On the right side, I have t sine theta divided by t cos theta. Oh, beautiful. One unknown is eliminated. We don't need that. Right? So, let's isolate the unknown. Out of this equation, what is the part or the value or the variable that we have no idea right? F. So let's keep F. Beautiful. So let's do this. And sine divided by cosine, what is that? Tangent. Tan theta times mg. Right? So we have another formula, by the way, which we can use. That would be F equals KE and of course Q squared divided by R squared. There's something else that we need to figure out. So something else creeps up. So how do we figure out R? Now let's figure out what is R. Obviously, this whole distance is your R. Don't confuse yourself because your particles are apart by a R distance. The whole distance is R. Okay. Remember, this here, this here. But let's say this part is our D. Now, the length of this string is given to us and it is 0.3 meters. This is given to us. So let's put them in a right triangle for us to see clearly. We have L. I say this is D. Now, this angle is given to us and that is 5 degrees, which is theta. So how do we find D? Exactly right. Exactly right. So we can use L sine theta because this is in the opposite. If this is on the adjacent, then you have to use the cosine. Now if you don't follow this, please, guys, after the class, stay extra time and get this sorted out. Yeah. This is the beginning of the semester. This is the time to figure these things out, because you'll be using this again and again and again. Okay? Okay, so now this is D. D is also equals to R by 2, half of R. If that's the case, R is going to be 2 times L. Does it make sense? Take the 2 to the other side. 2L sine theta is equal to R. Okay? That means I got this figured out. So what I'm going to do is I'm going to put this formula into this. Okay? So what do I have? I have K E Q squared. I'm going to keep R squared for the time being. But now I have a nice term to put where I vote is equal to tan theta times mg. So what is the unknown term? What are we trying to find? Q. So let's isolate the Q. So Q is equal to R squared tan theta mg divided by Ke. Take the square root. I'm doing so many steps at the same time. You can't follow me, stop and ask. Okay? What did I do? I took R to the other side. So in other words, you have to multiply both sides by R squared. And that's how I got it here. And I divide both sides by Ke, constant, right? So that goes to the bottom, right here. Tan theta mg stays as it is. I can take R squared out from the square root because this is a squared. So if I were to pull this out, what do I get? I get R, and then I have tan theta mg divided by Ke. Now I'm going to erase some of these. I think you have already written these, so no worries, right? So Q is equal to R is now 2L sine theta. So I put 2L sine theta and I have tan theta times mg divided by. If you want to plug in the values, now's the time. Okay. So I have 2.3 meters sine of 5 degrees within the square root. I have tan of 5 degrees times mass is given to us as, I think I may have erased that, right? So we have 2 times 10 to the power minus 4 kilograms times 9.8 meters per square second gravity divided by 8.99 10 to the power 10. I think let's get that straightened out. Oh, nice. Not negative.
No, it's positive.
Newton square, Coulomb square, meter square. Meter square divided by Coulomb square. Keep the units clear and correct. Okay, all the time. So now what? Just solve everything out and you can find what is Q. what you want to do is think about this problem and kind of follow it mentally. Okay, that is the most important. You will not get this in the exam. You will get something that may look like this, something that may be closer to this, but you won't get this from Dr. G. Okay? Okay, what is the value? Get your beautiful calculators. They have been alone without work during the fall, Christmas. Now's the time to let them work again, right? How much? It's a little bit long, unfortunately. So many terms in there. You should get 7.2 nano. Okay, we are going to start the other problems with you.